Patrick, thank you for that great introduction. And actually, it's a perfect segue into what we will be talking about today, which is mastering Apple's endpoint security. Now, I always like to start my talks by hopefully clearly articulating what I hope we will all learn today. So what we're going to try to do is move beyond the basics to really understand and unlock the full power of Apple's endpoint security, while also avoiding some of its nuances, its challenges, its pitfalls. Some of you here might be like, okay, well, endpoint security, that's like writing tools, programming, how does that apply to me? Valid question. Maybe one day you will be inspired, maybe after this talk, to write your own security tools. I would recommend it. But I imagine many of you also deal with vendors who want to be installing their security tools in the networks you manage, on the Macs you manage. And they hopefully will be using endpoint security, and hopefully they will be aware of the nuances that we will cover today. And so by you understanding these as well, you can ask the right questions. So we're going to start with some basics. What is endpoint security? Some of you who are familiar, this might be a little bit of a review, but the goal is to get everyone on the same page so that when we then transition into more advanced topics and some of the nuances, we're all still together. Patrick introduced me as the other Patrick, so no really further ado. I do, yes, work at the Objective-C Foundation, write a lot of free open source security tools. We also organize the OBTS Mac Security Conference and much more. More recently, I've co-founded W. We are building core macOS detection components that are designed to be integrated into larger security and EDR products. I'm also the author of the Art of Mac Malware book series. I'm mentioning this here because if this talk sparks your interest, there is a lot more content in these books. Specifically, chapters 8 and 9 are dedicated solely to endpoint security. The other good thing is, this is not a sales pitch because the book is 100% free online. So you can hop over to taomm.org and read both the second and the first volume. The first volume covers Mac malware analysis. The second is about creating and writing security tools for macOS. However, if you do decide to buy a printed copy, 100% of royalties are then donated to the Objective-C Foundation. So win-win. All right, let's dive into endpoint security, starting with some of the basics. So first question, what is endpoint security, or ES? Well, it's really an Apple framework just for third-party security tools. You might be thinking, okay, so what? This is like such a cool thing that I'm super passionate about because, as Patrick mentioned, more than a decade ago, I started writing free open source tools for macOS. And at that time, there was no dedicated security framework for that. So something as simple as writing a process monitor, for example, to authorize processes to ensure perhaps the user wasn't running anything that they shouldn't, or that malware wasn't infecting the system, that was incredibly difficult to do. There was just no APIs, no frameworks. So at that time, we had to jump through a lot of hoops, use Apple APIs, private frameworks in ways that Cupertino really wasn't stoked on and didn't support, but we had no other option. Now, though, with the introduction of endpoint security, third-party developers who are creating security tools for macOS rejoiced. So I often critique Apple, but this is one of the times where kudos to them. I'm so happy they finally did this. Now, we can see Apple's definition is a little bit more in-depth. It says it's a C API for monitoring system events for potentially malicious activity, et cetera, et cetera, et cetera. The good news is Apple does a pretty good job documenting it, unlike some of their other frameworks and capabilities. So if you pop over to their developer site, there's a lot of good information. There's WWDC videos on it. There are sample code. And macOS actually ships with a super useful utility called ES Logger that allows you to actually view the events that endpoint security can broadcast. So if you're brand new to endpoint security, I recommend playing around with ES. And we'll talk about how we can use ES Logger, for example, to understand when Apple adds or introduces new endpoint security events. Now, any of you that have actually spent a lot of time writing security tools using endpoint security, you will know that it's best just to skip Apple's developer documentation and dive straight into the header files, because for endpoint security, the header files are really the alpha and omega for all things related to endpoint security. So there's three main ones. You'll find them in the Endpoint Security folder under the SDK root: ES client, ES message, and ES types. And we can kind of see on the slide here, you can't really read it, but the purpose is just showing you that these header files contain things like ASCII flowcharts that really dive into some of the more nuanced topics of endpoint security. So they're super well commented, have a lot of great comments and gotchas. So if you ever get stuck, definitely check out the header files, and we will be referencing them a lot through this talk. Now again, you still might be wondering, okay, what's the point of talking about endpoint security? Well, and this is one of the main takeaways, and that is if you are building security tools for macOS, which I recommend we all should, it's a fairly fun activity, you should first be asking, or the very first question should be, can I use endpoint security? And the reason is this is Apple's recommended supported way to build security tools for macOS, which is great. It means they don't purposefully break it when new versions of macOS comes out. Also, they're continually making it more and more powerful, and so much so, as we will see in this talk, it is so powerful that even the most sophisticated advanced malware out there is going to generate events that endpoint security can pick up and deliver to your security tool, which gives us a very powerful detection capability, in theory even able to detect threats that we've never seen before. So, how do you write an endpoint security tool? Well, conceptually, it's really straightforward. There's two main steps. So I'm going to talk about conceptually how to do it, and then we're going to dive into some very brief code samples that you can treat as resources, but will also hopefully articulate better these two concepts, or these two steps. So the first thing we do is create an endpoint or ES client. This client, and we'll talk about this more, is created with a handler or callback block. Once you have that initialized endpoint security client, you tell endpoint security what events are of interest to you. And we'll dive into all the different events. But for example, say you're interested in observing when new processes are launched. Perhaps you want to check to make sure it's not the user inadvertently running malware. You are going to subscribe to the notify exec event. So once you've now subscribed to this event, anytime a new process is started anywhere on the system, by other system components, by the user, by an exploit, by malware, doesn't matter, endpoint security will deliver a notification message back to your client and the callback block to say, hey, just let you know, some new process just started. And as we'll see, a lot of metadata about that new process. So what are the events that you can subscribe to? If you look at the header file, there is a large structure with about 150 of them. And Apple is continually adding more, especially in new versions of macOS. There are two main categories, and we'll talk about both of these, but the first are notification events. These are events that happen after the fact. So we just mentioned perhaps creating a simple process monitor. If we do that and register for the notify exec event, anytime a new process is started, like I just mentioned, endpoint security will deliver an event to us. Two important caveats: it will be delivered sometime after the fact, so the new process will already have been launched. And also, there's nothing you can do about it, meaning the process is off and running. I mean, I guess you could kill it, but there's no opportunity to respond back to endpoint security to tell it anything about, for example, blocking the process. So notification events are great. They're good for passive analysis tools. Perhaps you want to build something to analyze some malware or just observe what's happening on the system. But the more powerful events are the auth events. And these events, endpoint security will actually pause or hold up the event while it asks you what you want to do. So there is a corresponding event for process spawns. It's the auth exec event. And if you register and subscribe to that, anytime a new process is starting, the operating system and endpoint security will actually pause it, come over to your client and say, what do you want me to do? Either allow or deny it. You can examine it, see if it's trusted, make sure it's not malware, and then you can respond back to endpoint security, either saying allow or deny. In many cases, there's both types of events. There's process, for example, notify exec and notify auth. But in many cases, there's just the notify event. For example, we'll see for TCC events, there's only a notify event. So in this case, there's no option to authorize the event. Okay, let's talk about creating an endpoint security client. There are going to be some code snippets here. Don't worry if you don't understand it all. You can always go back, use them as a resource. The goal is really to convey the concepts in a little bit more detail. So first we import endpoint security so we can use it in our code. We then create or declare the callback handler block. We'll talk about that a lot more in a few slides. And then most importantly here, we call ES new client. And this is how we initialize a endpoint security client. All subsequent endpoint security APIs will require this client to be passed around. It's kind of like a handle on Windows, et cetera, et cetera. Now, this is the first endpoint security API call you will make, and so it's very important to check the error codes. We'll talk briefly about all the prerequisites endpoint security tools must fulfill, but some of them are, for example, it has to be entitled, run with root privileges, and have correct TCC permissions. All right, so assume now we have declared and created successfully the endpoint security client. The next thing we need to do is tell the operating system what endpoint security events we are interested in. I mentioned there's about 150 of them. You're never going to register or subscribe to all of them unless you're building a full endpoint security monitor. It's basically what ESLogger does. Generally, though, you're going to be creating a process monitor. So then you're going to tell endpoint security, hey, I am interested in just process events. A file monitor, for example, file events, et cetera, et cetera, et cetera. So to do this, you invoke the aptly named ES_subscribe API, and it takes the client we just created, an array of events of interest. Here we're only subscribing to one event, the notify exec. And then you also have to give this API the number of events that are in this array. And the reason you have to do this is, if you remember on the first slide, Apple's definition said that endpoint security is a low-level C API. So when you pass, for example, an array to a C API, you have to tell it how many bytes or members it has, right? It's kind of more low-level than Swift or even Objective-C. And then again, once you're subscribed, anytime these events happen anywhere on the system, Apple and endpoint security will deliver them to your handler block. So let's briefly talk about what shows up in this handler block, specifically what is the message that endpoint security will deliver to your code that allows you to examine the event in more detail and in some cases take action. So the format for this is an ES_message_T structure. We can consult the header files and see a fairly large structure definition. I don't want to go through all the members of that. That would be incredibly boring. But I do want to touch on 2 or 3. Probably the most important is the responsible process. So again, this is going to be in every message that endpoint security delivers to your callback block when events matching the events you subscribe to happen anywhere on the system. So imagine we have created a file monitor. We've subscribed to file events. If anybody anywhere on the system creates a file, we'll get an alert, and the responsible process, as its name implies, will have the name of the process, whodunit. This is good, right? We can see, is this a system process creating a file? Or is this a malware creating a property list, for example, to persist as a launch item? We also have the event. This is important because you often use the same handler block for multiple events. So this tells you which event it's delivered to you, event type. And then there's also going to be event type specific data. So obviously, if it's a process event, there's going to be information about the newly spawned process. If it's a file event, it's going to be information such as the path to the file that was created. Now, let's finally dig into a little bit more about that handler block, which again is invoked for each matching event. You can do whatever you want in this handler block for notification events. These events are passive. Endpoint security doesn't care. So in this case, imagine we have registered for the notify exec event that will be delivered to us after the fact when a new process has been spawned. We print out the responsible process. That would be the parent in this case. And then in this case, we also print out information about the newly spawned process. Its PID, its path, its arguments, et cetera, et cetera. If this was a file event, we would do other things like print out the path of the newly created file, timestamp, et cetera, et cetera. Now, I did briefly mention some prerequisites, and I've dedicated a whole slide to them because they are very important to conform to, and in some senses, this is the most complicated thing about writing an endpoint security tool. First off is the all-powerful and much protected endpoint security entitlement, which is the com.apple.developer endpoint-security.client. Now, endpoint security is incredibly powerful. Basically, with it, you can see almost everything happening on the system. So there's some privacy concerns here. So Apple is not going to hand this out to everybody. So what you have to do is you have to log into your developer account and plead, beg for Apple to give it to you. Now, the good news is if you are a company building security tools and you have a reasonable reason why you need endpoint security, Apple now is pretty good at giving it to you. I only know one case, though, where they gave it to an individual, to Chaba, and he was writing security tools, but it was a long and arduous process because, again, Apple really doesn't want to hand out this very powerful entitlement to individuals, even if they are well-known writing security tools. And again, Apple now is a little bit better if you're a company, but I remember when this endpoint security came out, I had some friends at Malwarebytes, and they were stuck waiting 6 months for Apple to give them a security entitlement to use the endpoint security framework. But now I think it's a little better. So imagine that Apple has now granted you this entitlement. You are super stoked. There's still some prerequisites that you have to fulfill in order to deploy your software. Obviously, it has to be notarized and have that entitlement. It then also has to run with root privileges and have full disk access. This means the user is going to have to manually grant it, or if you're deploying it via MDM, you're going to have the correct permissions or profiles to grant it. So good to be aware of, otherwise your endpoint security tool will not run, and it will be blocked. All right, so that was a pretty quick but pretty deep dive into the basics of endpoint security. So again, just to briefly conclude that section, we create a client, we specify a callback block, and then we subscribe to events of interest that endpoint security will deliver to us, either notification events or authorization events. So those are the basics, and with that, you can start writing super powerful security tools for macOS. What I now want to talk about are some of the more advanced topics, but also some of the nuances that have personally tripped me up, and others as well. And the goal is, well, if you're writing tools, hopefully you learn from my mistakes or my shortcomings, and also the nuances that we'll cover, so that you can avoid them altogether. So let's first start with caching, which we'll see is an essential optimization, but has some nuances. So what is caching? So we talked about notification events, but there's also the authorization events. And again, recall endpoint security will deliver these events to you before the event has completed, before, for example, the new process is allowed to spawn, and it will wait for you to tell it what you want to do, either allow or deny. You do this by invoking the ES respond auth result API, and this takes the conclusion, allow or deny, and a flag. And the flag says, should this action be cached or not? If you tell it to cache it, all subsequent executions of that same process will not generate subsequent events. And you can see that's probably what you want to do most of the time. So here's an example of why you should use caching and why Patrick didn't, or when Patrick didn't, this Patrick didn't use caching and some of the challenges or issues it created. So one of the tools I create is called block, and it has a feature that I refer to as notarization mode. Notarization mode is super simple, basically blocks any process from spawning if it's not notarized. Now, macOS kind of tries to do this, but especially on older versions, the user could just like right-click and run, or even now you can kind of run it through the terminal. So malware exploits this fact to try to trick users into running non-notarized malware. The idea is that most legitimate software is going to be notarized, but even still, the vast, vast, vast majority of malware is not notarized. And why would it be? The malware authors don't want to give their malware to Apple before deploying it. So block basically says, hey, I don't care how it was run and exploit a user. If it's not notarized, no luck. I'm just going to drop it on the floor. And it does this by registering for an auth exec event. Anytime a new process is spawned or about to be spawned, endpoint security comes to block because it's an endpoint security client. Block checks the notarization status. If it's not notarized, it says deny, and endpoint security says cool and blocks the process. So super powerful, very good generic security tool to block a lot of malware. Now, don't worry too much about the code, but the main takeaway from the slide is block, for reasons unknown, Patrick not reading the documentation as well as he should have, did not actually cache the result. So you can see us invoking the ES-respond auth result API, but the last parameter, which is the caching flag, I set to false. This really didn't cause a problem normally, but then some users said, hey, I'm building large software projects, and block is like doubling the compile time. And I was like, that's not good. Let me look into that. Well, no surprises here, since I wasn't caching the response. When you did something like build a large software project, which on macOS will cause the compiler clang to be invoked again and again and again and again, if you don't cache that, Endpoint Security is going to send you a message for each invocation of clang. Block is going to run its code again to check if it's notarized, and that whole process is going to repeat, and it's going to slow the system way down. Gets a little bit more nuanced because I had another report that said when block is running, Jamf Protect is like crushing my system. And I was like, that's super weird. So I dug into it a little bit more, and this revealed one of the more problematic nuances of endpoint security caching, which is that it's global. And so it turns out that if any client does not adhere to caching, that basically invalidates caching for all other endpoint security clients. And you will run into scenarios where there are multiple endpoint security clients, right? Like someone might be running Jamf Protect, which uses the endpoint security framework, and block, which also does. So what was happening in this case, Jamf basically said, when a new process is being started, we're going to run some pretty resource-intensive checks. We're going to hash the whole file. We're going to do some Yara scans and much, much more. But then we're going to cache that. So we're never going to do that again. So that's OK, because it's only done once, right? Well, when block came along and didn't cache things because the cache is global, that basically invalidated the cache, meaning every new process was then re-reported to Jamf, which then would run all their checks again, which would slow down the system. So who's at fault here? Obviously, first and foremost, block, yes, should have done caching. I would argue Apple took a lot of shortcomings, or shortcuts rather, to create a global endpoint security cache that has this shortcoming. It's also worth noting out anytime a new endpoint security client starts, the cache is completely invalidated again. So this means even security tools like Jamf Protect, in my opinion, should also use their own internal cache, because if you're making big decisions based on endpoint security cache, which can be essentially invalidated by anybody else, that's a big assumption. So you should probably defensively code against that a little bit more. Really, main takeaway, though, is caching is super nuanced. And it gets even worse. So caching is very broad. At this point, you might be thinking, OK, I got it, Patrick. I should cache, otherwise everything slows down. Yeah, that's true, but as I just mentioned, caching can be broader than you think. So here's just one example. Caching is based on the binary that's being spawned. So if you examine a new process and you tell endpoint security that you want to cache the event, as long as that binary doesn't change, you will never be alerted again about that binary, which seems like a good thing. But what if that binary takes command line arguments, and those command line arguments can really influence the execution, essentially, of that process? Well, then you run into a problem. And we can see on the slide, imagine a developer has run bash and curl to download and install something from Homebrew. If an endpoint security tool sees that and caches bash and curl, when they're subsequently executed, even if the command line arguments change, for example, to install malware, endpoint security will not deliver a new message. It doesn't care about the arguments. So it's very important to understand this because you should not cache binaries where command line arguments control behaviors. For example, curl, bash, Python, etc. And this then segues nicely into a very next nuanced part of endpoint security, which revolves around scripts. So this is important to talk about because there is a lot of Mac malware that is distributed as scripts. Some recent examples, Joker Spy, Sigin, there are Python scripts, there's AppleScript scripts, there's Bash scripts, the whole gamut. And the reason why this is a little bit challenging to endpoint security is because, recall we talked about the responsible process. So when an endpoint security message comes in, what we can see is who is responsible for that. But in the case of scripts, that's just going to be the script interpreter. It's going to be Bash. It's going to be Python. That really isn't helpful to us. Those are trusted Apple platform binaries. What we really care, though, is more about the actual script, what is often running, so we can check, for example, is that malware or not. Fortunately, in original versions of endpoint security, there was nothing to address this. In the second version of endpoint security, Apple kind of ties the versions of endpoint security to new versions of macOS. So in version 2.0, they added a script member to the process exec structure. So now anytime a new process was spawned, there was a member, and if it was executing a script, this script field would be set and would be point to the script. That was super cool. So now in theory, we could write some very simple code that checks the version of Endpoint Security to make sure it supports the script member. And if it does, we could examine the script field, and if it's non-null, we could check to make sure it's not malware. Hash it, scan it, whatever heuristics we want. But more nuances, more limitations, kind of the theme of this talk. So here we have an example of Patrick running the Joker Spy malware. First, I run it directly, .sh.py. This generates a auth event, as expected, for Python. And in this case, the script member is set. This is perfect. Joker Spy is known malware, so I can check the script, see it matches a known hash, and I can block it by returning deny to endpoint security, and the operating system nicely blocks the malware. The user is protected. But what if I run it via Python? Yes, I still get an auth exec event, but it turns out the script member is not set. So in this case, the malware is allowed to run because I never see it. Well, if we go to the header files, there's a very small comment that says, this will only, the script member, be set if it's executed by the interpreter. For example, in the first case, .sh.py. However, if it's executed as an argument to the interpreter, yeah, good luck, we're not going to set this. And I'm like, really? All right, well, thanks for letting me know, but like, this is super half-assed, my opinion. So what to do? One solution, I'm not sure if this is a better one. You can check if the scripts, if the process, you're always going to get the process event. You can see if it's a script interpreter. And if it is, what you can do is you can perhaps scan all the arguments. So the first question is, how do we know it's a script interpreter? You have to create like a large list. It could be Bash, it could be Perl, it could be Tickle, it could be Python, it could be homebrew version of Python. It gets complicated. But if you see one of those, check the args. The other thing is, like, how do we know what argument is the script? All of these interpreters take variable command line arguments. The script doesn't have to be the first one or the last one. I just scan them all. Not ideal. Oh, and also, you don't want to cache the script interpreter because its arguments can change. So one solution, it's not ideal, but again, we have to be aware of the limitations in endpoint security and work around them. The next thing I want to talk about is a fun one, because if we mess this one up, Apple's going to nuke us, and that is authorization deadlines. So we've talked a few times about authorization events. To review, they're super powerful. The operating system will actually pause the event and wait till you respond. So you can see if you're writing a security tool, for example, to detect new malware, this is awesome. It gives you the ability, for example, to check every new process spawn, every new file creation, and ultimately tell macOS whether or not you want to allow it. Super cool. Obviously, Apple is like, okay, we're not going to give you forever because while we're waiting for you, like the user might be like, why isn't my application launching? So turns out if you take too long, Apple, Endpoint Security, will actually nuke you. It'll kill your Endpoint Security client and never restart it. Yikes. And you're like, okay, cool, well, I'll just respond quick enough, right? Like, I'll maybe not do some crazy cloud analysis. I'll be sure to respond quickly. But what happens if you're waiting for the user? Like, what do? So back to BlockBlock's case, remember it's notarization mode. If it detects a script or binary that is not notarized, it actually asks the user. It says, hey, just to let you know, do you want to allow this or not? And this is great. This was able to detect 0 days before Apple's patch came out, before anyone knew about the 0 day, because in the past, there's ways to sidestep notarization. BlockBlock didn't care. It basically said, hey, if you're not notarized, I'm not going to let you run, but I'm going to ask or alert the user. Well, if the user was like out to lunch or didn't respond to this alert right away, like what is BlockBlock supposed to do? Because again, if it waits too long, Apple will kill the BlockBlock process and never relaunch it again until the system is rebooted. Well, it turns out the auth events have a deadline, and this is great. If we go to the header file, we learn 3 things about the auth event deadlines. First, they are mock absolute times. Next slide, we'll talk about what that means. I had no idea. Number 2, probably the most important one, failure to respond means you will die. Okay, got it. And thirdly, deadlines can and do vary. So don't just read one and then treat it the same. We can prove that by writing a simple endpoint security client that just prints out the deadline. We can see that for system processes, it's currently about 3 seconds. For apps, it's 15. Like, that's pretty long. But again, you can imagine if the user doesn't respond in 15 seconds, you got to do something. Also, don't go on Apple forums and ask for longer deadlines. My favorite Apple employee, Quinn the Eskimo, I think he was joking, but he's like, every time someone asks to make it longer, we make it shorter. So I hope that he was kidding, but currently it's, I think, pretty reasonable. Okay, so let's talk about how to handle these deadlines, starting first with the deadline value, which recall is a mock absolute time. I didn't know what that meant. Apple says it's a value of a clock that increments. Cool. But what we really want to do is convert it to nanoseconds, because most of the APIs that can take action before some deadline expect nanoseconds. So I said, okay, super easy to convert from mock absolute times to nanoseconds, right? No, there's nuances. So if you read Apple's addressing architectural differences, which I highly recommend. No, it's super boring. This was released when Apple was transitioning from Intel to Apple Silicon, and they basically said, developers, you can just recompile your software, and we will compile it into ARM64. It will run perfectly, except for like 1 or 2 nuances. And one of those nuances is converting from mock time to nanoseconds. I'm not going to bore you with the details. You have to like take into account some time-based information. The good news is Apple provides a simple conversion function. Use it. Don't do your own mock to nanosecond times like I tried to do before, spending my weekends reading architectural differences document, because you'll get it wrong, and if you get the deadline wrong, you will get nuked. So this is one way to ensure a timely response. Again, don't worry too much about the code, but conceptually what it's doing is it's getting the auth deadline from the message. It's computing how much in the future that is. And then it creates a semaphore that fires just before that deadline. And so if the user hasn't responded, for example, in this case, block, the deadline semaphore will fire and say, hey, we got to respond. Apple's about to nuke us. And in this case, it just allows the process. I'm not sure there's a better way to do. You could also just deny the process, but that decision is up to you. One takeaway, don't try to cut the deadline too close. It's always going to take a few nanoseconds to respond. There might be a context switch. The system might be busy. I've noticed in some cases that Apple will kill you before the deadline. So the best bet is to calculate the deadline, say it's like 15 seconds, and then try to respond within like 10. Again, by setting a deadline semaphore or something. But again, really try to respond before, otherwise Apple will kill you. All right, so those are deadlines and authorization events. The next thing I want to talk about is mute and mute inversion. This is a very powerful capability of endpoint security, but at least to me, makes my head hurt a little bit. So let's dive in, and I hope that I don't lose y'all the way. So muting is actually very easy to understand. So imagine we're writing a file monitor with endpoint security. We have told the endpoint security subsystem that we want to subscribe to file events, file open, file write, file delete, et cetera, et cetera. We compile this, we adhere to the prerequisites, and we run it, and immediately we get gazillion file events. This is like streaming the system log with debug messages. There's just a gazillion of them. And this is because there's a gazillion legitimate file events that are happening all over your system all the time. So this is kind of overwhelming, and at the very least, you probably want to start filtering out or muting certain events that are not of interest. So for example, if you're running your file monitor via the terminal, anytime you print to standard out, that's going to generate a file event, which then your file monitor is going to print out and generate another file event. So clearly, at the very least, we want to mute ourselves. We want to tell endpoint security, yo, I told you I'm interested in file events, but please ignore me specifically, right? So as we will see, you can mute arbitrary processes, and then you can also mute the events as well. For example, you might want to mute or ignore file events that are being written to the temp directory. You're like, I don't care about that. So muting is, again, the technology, the capabilities we use to tell endpoint security to either ignore certain processes, responsible processes, all events from them will be ignored, or specific events based on, for example, their file path or destination. So first, let's talk about muting processes. We can use the aptly named ESMute process API. The one challenge about this is it takes an audit token. Audit tokens are just a more modern, more secure way to refer to a process. They kind of replace PIDs. But the question is, how do I get a PID of how do I get an audit token of myself or an arbitrary process to mute? Turns out we have to kind of go into some low-level mock APIs. Again, this code is just kind of for resource, but basically we can make a mock API, give it a PID, and it'll give us the audit token that matches that PID. And then we can take that audit token and we can give it to the ESMute path API to mute the process. Sorry, the ESMute process API. Now we can also mute the process based on the path. So if we have the path to our own process, or perhaps we want to mute Spotlight, for example, we can just give it the path to that and mute it as well. So here's an example of that. And again, the ESMute path API that Apple documents. So that's how you mute the responsible process. What if you, as I mentioned, want to also mute specific events, say files that are being written to the temporary directory? Well, that's where you still use the ESMute path API, but as its last parameter, it takes a mute type. And there's 4 different types. The first 2 are for muting the responsible process. The last 2 are for muting the event. Both of these types either can be the underscore prefix or underscore literal. Prefix means it'll match the prefix. So you can say, for example, ignore everything that falls under temp. Literal is the full path. So it's kind of nice you have some flexibility. One nuance, endpoint security, being a low-level C API, does not work on paths that are symlinked. So actually on macOS /temp is symlinked to /private/temp, I think. It's symlinked to something else. So if you actually pass /temp to the muting APIs, they won't fail, but you'll still get events because under the hood they're actually being symlinked. So this is good to be aware of. Just make sure you resolve any symlinks before you pass the paths to endpoint security. Again, another nuance. Okay, so that's muting. That's hopefully fairly straightforward. Let's now talk about mute inversion. So imagine you want to do the opposite. Instead of subscribing to events from all processes or file events from the entire system, what if you want to just do one directory or from one process? Well, Apple eventually was like, yo, this is a good idea. So in later versions of Endpoint Security, they added mute inversion. And it basically allows you to do just the opposite and say, I want to focus either on one process or, for example, one file directory, events that match. A very practical conceptual example, and we'll look at some code to implement this, could be perhaps blocking or protecting against macOS stealers. Stealers are very prolific. They're probably the most common family of Mac malware targeting Mac users these days. The idea is once they get on the system, they, as their name implies, steal all the things and exfiltrate it. They're reasonably difficult to detect because they don't persist. Sometimes they're notarized. But if we look at what they do, they almost always go after, for example, cookies, auth tokens, the keychain, et cetera, et cetera. So using endpoint security and mute inversion, we can create a security tool that, for example, says, I'm going to monitor the, for example, cookie directory for Chrome. And here's some example malware code that is going into the Chrome directory to steal cookies. And what our security tool can do is use mute inversion to basically just watch that one specific directory, or a handful of directories, and authorize who is accessing those. And if it's the browser, that's fine. If it's Finder, if it's user, that's fine. If it's Spotlight, that's fine. But if it's some unauthorized, unrecognized process, that's something we probably want to block. So this is an example where mute inversion can really come in handy. So how do we actually implement mute inversion? Well, the first thing we want to do is we call the ESInvert muting API. And the reason we do this is Apple made a pretty smart decision. They said, we already have all these muting APIs, so instead of writing brand new ones to handle mute inversion, why don't we just add one API that flips muting to invert it, and then the user can invoke, or the programmer can invoke the same muting APIs, but now they will be inverted. And so that's exactly what we can do. And I'll show that in code because for me that was a little confusing because you're calling the same mute APIs, but now instead of muting, they're doing mute inversion. So it all starts with this ESInvert muting API, and again, there's different types. We can see, though, there's types for if you want to mute, invert the process or the path. Now, there's one other thing to talk about mute inversion, and that is the default mute set. And again, this is not something that's very well documented, but it's super important to be aware of. So, turns out, when you subscribe to Endpoint Security events, Apple gives you everything, but not actually everything. There is a subset of system-critical binaries that Endpoint Security mutes by default. Apple says, no, we're not giving you the events. Not because they don't want you to see them, it's because if they did, it would cause deadlocks, timeouts, crush the system. So they say, okay, we're gonna make sure that these processes are never generating endpoint security events because they're too time critical. And that's all well and good. The problem, though, is when you invert muting, the first thing it does is actually unmute everything, which means now the default mute set is unmuted, which is not what you want. So what Apple says you should do is call ES unmute all first. That will temporarily unmute the default mute set. And then as soon as you call mute inversion, it will re-mute it again. TLDR, the default mute set will almost stay fully muted, which is what Apple recommends. Again, nuances. So let's look now at some code. Again, we can use this just as a default that shows how you would do this mute inversion logic. It takes a while to talk about, but actually the code is super straightforward. So at the top of the slide, we are getting the directory of the user's documents. Imagine we're building a tool that is protecting the user's document directory from stealers, ransomware, whatever. We basically want to authorize who has access to the user's document directory. So we create an endpoint security client. We subscribe to the auth open event. This is the event that will allow us to authorize file opens. And then comes the mute inversion logic in the highlighted box. We first unmute all target paths. This is only because of the default mute set, which now we know all about. We then invert muting, because we want to do the opposite. We only want to watch one specific directory. And then we call the ES mute path API. This is now going to do the opposite because we've inverted muting. So instead of muting what we specify, it's going to mute everything else. Again, this is where my head kind of starts to hurt, but hopefully I've made a stab at explaining this. And then ultimately, we subscribe. Now, anytime anybody, malware, the system, the user, tries to open files in the document directory, we will get a notification. We can examine who's doing it and ultimately allow or deny it. Here's an example. If we run this, we're watching the documents directory. If Finder browses into it via the user, we see Finder is trusted. We get a notification. We allow it. If a stealer comes along, I forget exactly what stealer this is, but it's one of the more common ones, probably Amos or something. We can see that this generates an endpoint security event because someone is trying to open a file in the user's document directory. We can examine who it is. We can see it's not trusted, it's unauthorized, it's new, it's not notarized, however you want to make that decision, and ultimately block it. And since it's an auth event, endpoint security will not allow that event to happen. So, like, we've kind of solved stealers, at least conceptually. All right, I want to kind of start wrapping this up by talking about what's new, because Apple is always improving endpoint security. The most common thing they add is new events, and you can figure out what new events are being added by looking at the header file that has the long list of events. What Apple does is they will add them at the end and nicely comment telling you what versions of macOS are supported. So this is actually a screenshot from the header file. We can see in macOS 13, they added some new XProtect events. Super awesome. You can now programmatically subscribe to when XProtect detects malware on the system. BTM, this is persistent events. You can now register for these as well. Super cool if you're building like a persistence monitor. And then in 15.4, they added TCC modify events, which we will talk about. Super important, though, these are not backported. So what you need to do is if you are using these new events, which you should be on newer versions of macOS, make sure to wrap your code in the appropriate runtime safety checks, because otherwise if it runs on an older version, like if the user runs it, it might crash. So it's always good to have defensive coding. So I briefly want to talk about Apple's new TCC event, because it's super powerful, something I've been begging for many years. I'm sure many of us, all of us know about TCC. It is what protects, the the downloads directory, the webcam, the photo book, address book, et cetera, et cetera. Malware is now aware of the fact that macOS is not going to give them full access even if the user runs them. So what does malware do? It asks very nicely to the user, hey, in order to run, I need full disk access, or please let me access your files. And unfortunately, some percentage of users are going to acquiesce, especially if they trust the software, if they don't realize it's malware. On older versions of macOS, via Endpoint Security, we as third-party security tool developers had no insight into this user faux pas, which sucked. But as of macOS 15.4, Apple added a new endpoint security event, specifically the Notify TCC Modification event. And when this event fires, we get a huge structure that has all these types and members that weren't really documented, and I didn't know what they were. So what I normally do, and what I did, is, come on, here we go, use ESLogger. So we mentioned ESLogger at the beginning of the talk. It is a built-in utility of macOS, and it allows you to subscribe and stream endpoint security events without having to write any code. Super dope. So here, for example, on a macOS 15.4 box that had the TCC endpoint security event, I could use ESLogger and stream events. Then I could execute some malware that modified TCC, or as the user, pretend to do what the malware said. And Endpoint Security ESLogger would print out then the new TCC event with all the information filled in. So we can see the responsible process. It always appears to be the TCC daemon. So in this case, that's not super helpful. What is more useful here is what access was granted. Here we can see it's full disk access, or FDA. We can see the subject of permission. This was the application or program that was granted that access. In this case, it was terminal. And then finally, we can see the instigator. And since the user did this because the malware told them to, they went into system preferences and clicked enable full disk access for terminal. And so that is reported to us as well. So with an understanding now, what we can do is programmatically re-implement this in our own security tool. Again, don't really worry about all the code, but this is how, given a TCC endpoint security event, you can pull out all those pieces of information from the message that we showed on the last slide, and then use that for detection, reporting, et cetera, et cetera. The last new thing I want to talk about was added in macOS 26. They actually didn't add any new events, but they added this new CS validation category. This is added to process events, so super, super cool. This means that for any and all endpoint security messages, you can see code signing information now, more detailed code signing information about the responsible process. And if it's a process exec event, you can see the child process that's about to be spawned. You can get all this great information, basically telling you where it was signed from the App Store, developer, Rosetta, et cetera, et cetera. Why this is useful: in the past, security tools such as mine, for example, Block, would make different decisions based on who signed it. Now, endpoint security always said, hey, something was signed or not, but it wouldn't say it's from the Mac App Store, or it's from a developer, or it's ad hoc. You could see we're going to trust apps from the Mac App Store probably a little bit more than something is ad hoc signed, for example. Previously, you could figure that out yourself, but macOS, Apple actually always knew that, right? When you launch an app from the App Store, Gatekeeper doesn't like run a bunch of checks and block it, whereas if it's from the internet and it's signed with a third-party developer ID, it will. Now, though, Apple propagates that information into endpoint security messages, which means tools that previously did that can get rid of all the code that was both somewhat resource-intensive but also complex, and now just use the additional information that endpoint security thankfully gives us. All right, the last thing I do briefly want to touch on the limitations of endpoint security, because you might think it's a panacea, and it almost is, but there's a few things that we should be aware of. First and foremost, some of the events aren't as comprehensive as we like. We just talked about the TCC events. First and foremost, it's only a notification event. There's no way for us to block TCC because there's no TCC auth event yet. Also, the TCC event that's delivered is only when TCC permissions are modified. This means when malware like Joker Spy runs, it queries to figure out what TCC permissions it has. that doesn't generate any endpoint security event. Personally, I would like that. If something's querying to figure out what TCC access or permissions it has, I want to know. It might be legit, but it also might be malware. Similarly, the WinTail or WinTape malware tries to execute the screen capture utility to take a screenshot. This is blocked, which is good, but it doesn't change any TCC permissions, so nothing is delivered to us. Again, I personally would love it if endpoint security was like, hey, something tried to take a screenshot and we blocked it. That would be super, super useful. Also, by design, endpoint security only triggers on new events. It's a real-time monitoring framework. That means once your security tool is installed on a new system, something that's already there is probably not going to be detected. So you're probably going to have to do things like enumerate persistent items yourself or dump the TCC database yourself. So I wouldn't say this is a shortcoming of endpoint security. It's outside its scope, but just be good to be aware of. Also, endpoint security, by design, doesn't cover everything. For example, if you want to monitor network activity, you do that with the network extension framework. Endpoint security does not do that. All right, conclusions and takeaways. We're going to wrap this all up. So, first and foremost, endpoint security should be your bestie. If you are building security tools for macOS, use endpoint security. It's insanely powerful. Apple supports it and improves it all the time. Also, make use of its advanced capabilities. Make use of caching. Make use of mute inversion. This will make your tools not only more powerful, but more efficient. But really be aware of the nuances and limitations because Apple doesn't really talk about them, and they will bite you in the butt if you are not aware of them. I briefly also just want to mention the Objective-C Foundation. We do all sorts of really cool stuff from the OBTS conference, student scholarships, student trainings, et cetera, et cetera. So if you're ever interested in learning more about that, you can pop over to our webpage. And then finally, I also want to thank the Friends of Objective-C. These are the companies and products that support the organization. This is why the books are free. This is why we were able to have so many student scholarships come to OBTS. This is why I can be here on stage talking about that. So if you know anyone that works at these companies, give them a high five. All good things. Lastly, I did want to briefly mention some super useful resources. I have talked a long time about endpoint security. In some senses, we've only scratched the surface. So if you're interested more, definitely check out the books I mentioned and check out some of the resources here because they will definitely help get a little further. Perfect. So I have about a minute. So if there's any questions, I usually try to go right to the end so I don't have to answer questions. No, I'm kidding. But we have a minute or two for questions, and then I will be around here because clearly I'm very passionate about talking, and I would love to chat more if there's any questions. So are there any questions about any of the endpoint security stuff? Just don't ask about mute inversion because it makes my head hurt.
Could you just mute us?
I mute inverted you. Uh-oh, it's going to be a hard one.
Can you combine somehow regular muting and mute inversion? So when you want the combination of the two?
Yeah, great question. So you can actually create as many endpoint security clients as you want. So I haven't played around directly with mute and mute inversion. What you can do, though, is you can mute processes and mute invert events at the same time. If you did both, remember that flow chart that I showed you at the beginning in the header files? This is a massive flow chart that Apple breaks down, and kudos to them for documenting exactly the process of what endpoint security does if it encounters multiple clients with muting and mute inversions. I haven't studied that flow chart. I would point you to that because there are definitely some nuances there, but I feel like the flow chart would, you can follow like A, B, C. But it is a good point that you could have multiple clients doing multiple things in the same process, and in theory, that should work. Great question. Anything else?
Well, time's up, I think. Thank you very much.
Thank you.